Okay, friends. So, welcome to session number 4 for private 5G networks design, planning, and optimization. And again, thank you so much for joining today's session. And today we are going to continue our discussion on CBRS and understands its architecture, spectrum sharing model, SAS, CBSDs, and some of the key use cases. So, this is the agenda. So, as you know that topic number 1, 5G building blocks for private networks is already covered. Then we have gone through the mastering the basis of private networks, and that is also done. And private network architectures component is also done. Enablers is also done. So today we'll try to complete CBRS for private networks, and we'll try to get some examples of real world 5G industrial deployments. Like in some of the industries, they use R dot. Some of industries they use Nokia's and DAC, right? So we'll see the real world industrial deployments. So I will try to complete these two topics today. And before jumping to the session, you know very well that for 3GPP, for private networks, I follow two basic specification. One is TS 23.501, which is for private networks architecture. Then we have TS 23.502, which is for the procedures. Okay. So you should remember these two specifications. Again, friends, this is Gaurav Goyal. Thank you again for joining this session and hope you will find this session useful and informative. Just a quick introduction about myself. I have more than 20 years of experience in telecom industry, working with operators and companies such as AT&T, Verizon, T-Mobile, Dish, Infovista, etc. So in Infovista, I worked as a product manager. So it gave me, in addition to RF engineering, it gave me chance to have customer interaction, understand their needs, convert those needs into simple words, and then give it to the design team and then provide solutions. So I started my journey with 2G and then worked with various other technologies like 3G, 4G, LTE, and 5G as well. Currently, I am focused on 5G, 6G, NTN, private networks, Python, IPS DAS, and also I'm preparing for my PMP certification as well. And before we start, I shared a few links. So please check if you can open them. And if yes, can you please write yes in the chat box? Are you able to open those links? So before we move forwards, I would like to share one of my favorite quotes from Albert Einstein. The only source of knowledge is experience. So we can learn a lot from books and training, but real understanding comes from when we apply that knowledge in real projects. So these iCards represents my journey from 2G to 5G and now into private 5G, NTN, AI, and 6G as well. So every project has taught me something new. So today I will try to share not just the theory, but also some practical knowledge and real world experience. So like in every webinar, let's quickly go through a few quotes that I personally like and would like to share with you. So one of them is success is like an iceberg. So what people normally see is the result. They see the achievement, they see the certification, they see the success, awards, all these things they see. But what people don't see is everything behind it. It may be the hard work, it may be the sacrifice, it may be the failures, it may be the sleepless night, it may be the growth mindset, it may be the time management, failures, discipline, persistence, all these things. The same applies to our telecom careers as well. So technology keeps changing. So we have to keep learning, adapting, and improve ourselves. So remember, success is not just the final result. It is a journey and hard work behind it. So keep learning, keep growing, and never give up. And here is another quote that I really like. Always do your best, no matter the size of your audience. So I really believe in this. So whether we are presenting to one person, 10%, or hundreds of people, our effort and commitment should remain the same. Even if only one person learns something valuable from our session, your efforts has made a difference. So always give your best. Focus on the quality and never measure your effort by the size of your audience. And here is the other message. I strongly believe invest in yourself. Technology keeps changing, especially in telecom. So never stop learning and never lose your curiosity. Keep reading, take some courses, learn from experienced people, and most importantly, keep trying new things. The knowledge and skills we build today will create opportunity for us tomorrow. The more you learn, the more you earn is the right saying. So remember, the best investment you can make is an investment in yourself. So keep learning and keep growing. Again, I request in every class, so please do not do any kind of multitasking. Please mute your audio connection and please put all the notification on the silent mode, because there is no such thing in the world called multitasking. So if you want to take something from this session, please do not do any kind of multitasking and stop any kind of social media, WhatsApp, Facebook, YouTube, etc. So these are the topics we have already covered in our previous sessions, like 5G building blocks, what are the motivation behind it. We have checked the various kinds of RAN, UE, core network, how they are connected with each other, how communication evolved. All these things we have already covered in our previous sessions. After that, we have seen the 5G use cases as well, like EMBB, MMTC, URLLC. All these things are already covered in our previous sessions. Then we have gone through all the user scenarios as well, all the building blocks, what are the new things that were introduced, what are the better things as compared to LTE, what are the 5G capabilities in terms of 8 points or this Viber chart. So all these things we have already covered in our previous sessions. Also, we have seen the new thing which is introduced, subcarrier spacing. Like in LTE, subcarrier spacing is fixed, which is 15 kilohertz. But here it can be 30, 60, 120, 240, and so on. This also we have discussed, and this is one of the most important feature in 5G. We have checked how OFDMA for 4G is different from 5G, how cyclic prefix is introduced. All these things we have already covered. After that, we have seen what is private networks. What are the four important benefits? So benefits, we have checked that it provides high device density, latency is low, high performance, and the secure communication. So these are the four important benefits of private network that we have already discussed. So private networks basically provide a dedicated network to that particular factory or the enterprises, right? Dedicated coverage. And we have seen the history of private networks that it is not new. It was already introduced many years back in terms of PBX. Also, we have seen various architecture for private network. It may be all things in one enterprise like E node B, GC, or it can be RAN is shared between private and public, or core can be shared, but the one slice is given to private networks. That also we have seen, and we have seen that private networks are nothing, but they are just small cells. They are the miniature version of the private. So private networks are just the miniature version of the public cellular network. This also we have seen in detail. Also, we have seen the Wi-Fi. Like so, Wi-Fi provides coverage, but that can't be reliable for large area, right? So that also we have seen. We have seen the differences between LTE and Wi-Fi, right? So coverage large area with fewer base station, but we have require large number of access point in case of Wi-Fi, even to cover a small area, right? Mobility is also excellent in case of cellular. Security is very better in case of LTE as compared to Wi-Fi, right? So these are the few things. And coverage, you can see that better penetration through walls, right? So capacity can be increased with the help of very low number of devices, but capacity is very limited in case of Wi-Fi. All these things we have discussed in detail, right? Then we have discussed private 5G and their enablers. That also we have gone through. Edge computing, multi-access edge computing, network slicing, enablers, all these things we have gone through. So that is available in the video recording, and I have shared that links with you, right? So let's jump to the today's session. The topic for today's session will be CBRS agenda, right? So let's go to CBRS. One second. All right, friends. Today we are going to talk about CBRS, which is Citizens Broadband Radio Service. So first we'll understand what CBRS is, why it is important, especially for private LTE and private 5G networks. Then we'll discuss the three types of CBRS spectrum access. It can be incumbent, it can be PAL, or it can be GAA. Next, we look at the CBRS network architecture and the main components. So we'll discuss about CBSD, which is radio or the base station equipment using CBRS spectrum. And we'll also go through the SAS, which is spectrum access system, the system that decides the CBRS frequencies that CBSD can be used. Also, we'll go through domain proxy, ESC, all these things. And after that, we'll look at some real world CBRS use cases and the industrial applications. So these are the 9 topics we'll try to cover in this particular session. So what is CBRS? So CBRS stands for Citizen Broadband Radio Service. It operates in the 3.5 gigahertz to 3.7 gigahertz band. More specifically, it operates between 3.55 gigahertz to 3.7 gigahertz. And it uses TDD, time division duplexing. And you know very well, in TDD, the same spectrum is used for uplink and downlink at different times. But in FDD, we use separate frequencies for uplink and separate frequencies for downlink. But here in TDD, same frequencies can be used, but at different times. So time is the main thing in case of TDD, but in FDD, frequency is the separation, right? So the main idea behind CBRS is spectrum sharing. So spectrum is shared between 3 classes. One is incumbent class, second one is PAL, which is priority access license, and third one is general authorized access. So incumbent has the highest priority. Priority access is the second highest priority, but it is the paid license. GAA has the third priority, but it is free, right? So every class has its own advantage and its own disadvantage. Again, CBRS is Citizens Broadband Radio Service, and it is established by FCC, right? And 3 tiers of breakdown. One is incumbent, one is PAL, and one is GA, priority access license, and the general authorized access. So what are the benefits of CBRS for wireless carriers, cable operators, and the enterprises? First of all, for the wireless carriers, so with the help of CBRS, we can improve the capacity by adding a new spectrum, right? And it has bandwidth of around 150 megahertz. And after that, cable operators also offload their traffic and they can improve the capacity. And then both wireless carriers and cable operators take the benefit with the help of fixed wireless access. So at some places where fiber is difficult to reach, we can take the advantage of CBRS. Also, enterprises uses this spectrum to build their own private network. So they are they have not to be dependent on AT&T, T-Mobile, or Dish for their network. So with the help of CBRS, they can have their own private wireless network. And this is very important because with the help of own private networks, latency is reduced, right? Capacity is improved, coverage is improved, performance is improved, right? And it is a dedicated network, right? It will be a dedicated network and it will be highly secure. So with the help of the CBRS, private networks can flourish a lot. So this is the history of CBRS. So in 2010, use of 3.5 gigahertz was identified by NTIA. In 2012, FCC promote this band that enable more efficient use of radio spectrum, small cell, and the spectrum sharing. In 2016, CBRS Alliance was formed. In 2020, FCC authorized 4 SAS administrators who authorized CBRS for commercial use. Then we have auction in 2020, and in 2022, CBRS operates below the C band. Right? So this is the brief history of CBRS band. And as we have discussed, there are three tiers of CBRS band users. One is incumbents, which has highest priority. Then we have PAL, which is priority access license, which can be purchased. And then we have GAA, which is generalized authorized access, and these are free. this license is free to use. So most of the private network use GAA. So the first tier is incumbent. So incumbent, as I said, will have the highest priority, and it is basically used for federal incumbents, Navy, all these things for use. So they use the full band between 3.55 gigahertz to 3.7 gigahertz. For example, for US military radar, can be between 3.5 gigahertz to 3.7 gigahertz. For fixed satellite stations, it can be between 3.6 gigahertz to 3.7 gigahertz. For wireless ISP, it can be between 36.5 to 3700 gigahertz. So depending on the use case, we may have different frequency allocated, but in short, you can say that incumbent will be the highest priority. And whenever incumbent users are there, it will override PAL and the GAA users. Second one is priority access license, or it is also called PAL. So it is a paid license, and this can be obtained only through auctions, and it has it has more priority than GA, but less priority than the incumbent. And each PAL guarantees a 10 megahertz channel for a 10-year terms. But the thing is that for each county, there can be maximum 7 PALs. So maximum 7 70 megahertz can be assigned to a one county. And it is not assigned full band between 3.5 to 3.7 gigahertz. It can operate only between 3.55 gigahertz to 3.65 gigahertz. Okay, this is also important thing we should remember. Then we have general authorized access. So in most of the private industries or factories or manufacturing plant, this is the used. So most of the private industries, GAA is preferred because first of all, it is free of cost. You don't have to pay anything for the license. But the thing is that it has least priority. So at a particular location, if incumbent is present or PAL is present, in that case, GAA will have to stop using that particular frequency, right? So it is least priority. So it has access to all channels that are not assigned and in use by the higher tier, which is incumbent and the PAL. So if no incumbent are used, GA are granted 8 10 megahertz channels. So maximum 80 megahertz in a particular county. And as I said earlier, GAA operates on channels not used by incumbents or PAL users and must accept interference from incumbents and the PAL users. Okay. Next one is spectrum sharing ecosystem. So now let's understand spectrum sharing, which is one of the most important concepts in CBRS. So simply put, spectrum sharing means that multiple users or networks can use the same spectrum without interfering with each other. So instead of giving the entire spectrum to one operator, the CBRS band allows different users to share it in organized or a controlled way. So to make it possible, several components work together. So one is CBSD, Citizen Broadband Service Device. So these are the CBRS radios or base stations that provide wireless coverage. Then we have domain proxies. So it acts as a middleman. So when there's many CBSDs, we'll talk in detail in next slides. Whenever there are many CBSDs, generally CBSD interact with SAS. But when there are many CBSDs, they don't interact directly with SAS. They interact with SAS with the help of this domain proxies. Then we have this EMS element management system. So it is used to monitor, configure, or manage the CBSDs. And this component is optional but very much useful. Then we have this EUD, end user device. It can be your cell phone, it can be your laptops, tablets, cameras, robots, AGVs, anything. Then we have this ESC, environmental sensing capabilities. So it monitors for the military radar. So if radar is detected, it immediately informs SAS, and SAS will told CBSD to free that channel for the radar, right? And then we have FCC database. So it provides information about the licensed users and the protected areas. And last, we have SAS, which is most important because it acts as a brain of the system. It decides who can use which frequency and when. So if you look at the diagram, you can see that SAS is at the center of the ecosystem. It communicates with the FCC database, ESC, domain proxy, and all these CBSDs to ensure that everyone shares the spectrum fairly and without causing harmful interference to any channel, right? So now look at the three key components that make CBRS spectrum sharing possible. So what are the three main components? One is SAS, one is ESC, and one is the domain proxy. So first one is the SAS. As I said that it acts as a brain of the system. So think of SAS as a traffic controller of the CBRS. So it knows which spectrum is available and it assigns channels to the CBSDs. It manages interference and most importantly, it protects higher priority users such as Navy, Federal, so that they don't have any problem in accessing the network. And as I said that incumbent is always the highest priority. So simply you can say that SAS decides who can use which frequency and when he can use that frequency. Second one is the ESC. You can say that ESC is the eyes and ears of the system. So ESC sensors monitor for protected federal radar activity, mostly in the coastal areas. So when protected radar is detected, the information is sent to SAS. Now SAS can then instruct different CBSDs to move to another channel or stop transmitting as required. So again, whenever ESC detects something, it informs SAS and SAS take action based on the ESC information. The third one is the domain proxy. As I said earlier, it acts as a middleman. So instead of every CBSD independently handling all SAS communication, the domain proxy can coordinate communication for the multiple CBSDs. So it helps with channel request, receives assignment, communicates them to the proper CBSDs, and reports information back to the SAS. So remember, domain proxy simplifies communication between CBSDs and the SAS. So these three components are very important, and together these components allow CBR spectrum to be used dynamically while protecting higher priority users and minimizing the harmful interference. Then we have this CBSD, Citizen Broadband Service Devices. So a CBSD or citizen broadband service device is simply the radio or a base station. So it provides wireless coverage in private LTE or private 5G network. So think of it as a small cell. So it connects user devices such as smartphones, laptops, tablets, scanners to the network. So every CBSD must register with the SAS Spectrum Access System before it start transmitting. The SAS assigned it a frequency and transmit power to avoid interference with other users. And it must be careful which channel is free and which channel is not free. That is given by the SAS. So CBSD are divided two categories. One is A and one is B. So first one is category A CBSD. So it is basically used for indoor enterprise networks such as offices, hospitals, warehouses, factories, shopping malls, campuses, etc. And it can be installed indoor or outdoor as well. And maximum transmit power is 30 dBm and its height above average terrain is maximum 6 meter. What is HAT? HAT is height above average terrain, right? Then we have category B CBSD. So they are designed for large outdoor coverage and they are commonly deployed in industrial sites, large campuses, ports, utility networks, all these things. And their characteristics are like they are mainly used for point to point and point to multi point activity. And their maximum power can be 47 dBm EIRP. So whenever you are designing a private LTE or private 5G network, choosing the correct CBSD category depends on your coverage area, deployment location, and the power requirements as well. So now look at the basic requirement for installing and operating a CBSD. So this is very important when you design private networks. So as I said earlier that a CBSD must always be able to communicate with the spectrum access system, which is SAS. And the SAS may send instructions such as change your frequency, reduce your transmit power, or stop transmitting at all if PAL or GAA is present. The CBSD must follow this instruction within the 5 minutes. It should be this quick. This ensures that spectrum is shared safely and without causing interference. Then we have this location requirements. So the SAS always needs to know where CBSD is located. If the CBSD is moved to a new location, it must report its new location to the SAS within 60 seconds. This is very important because spectrum availability depends on the location. Then installation guidelines. Since category A CBSDs are not that big, so it can be installed without certified professional installer. But to install category B, it must be installed and certified by a CPI, certified professional installer. And it can't be operated until CPI verifies and register the installation. So CPI is there to ensure many things like CBSD is installed at the correct location, the antenna height is correct, the antenna direction is correct, so the transfer power follows FCC rules or not. The installation information is correctly registered with the SAS. So all this information is taken care by CPI. So CPI is very important, at least in the class B category. So these categories help ensure that all CBRS users can safely share the spectrum without causing harmful interference. So again, the CBSD or Citizens Broadband Radio Service Device. So they are commonly divided into two categories. One is category A and one is category B. Category A is the lower power CBSD. It is commonly used for indoor deployments. For example, inside a office, warehouse, hospital, manufacturing facility. And it can also be deployed outdoor subject to the applicable installation requirements. As you can say that maximum ERP for category A is 30 dBm per 10 megahertz and the maximum power spectral density is 20 dBm per megahertz. The category B can go up to 47 dBm EIRP with a maximum PSD of 37 dBm per megahertz. So naturally, category B provides much larger outdoor coverage compared with category A. Do you know the relation between PSD and EIRP? Okay, thank you. Yes, you are right. So PSD is equal to EIRP minus 10 log 10 bandwidth in megahertz. Right? Suppose our EIRP is 47 and our bandwidth is 10. 10 47 minus 10 is equal to 37 is the PSD, right? This way you can calculate the PSD value. So formula is EIRP minus 10 log bandwidth in megahertz. CBSD network architecture. Now, so now that we have understand category A and category B CBSDs, so now let's look at the overall CBRS architecture and see how these components work together. So first, on the left side, you see end user devices. It can be mobile device, smart home, industrial equipment, surveillance cameras, all these things. Then we have CBSDs. As I said that CBSDs is a term used in a private network, but in general terms, you can say that it is small cell, base station, right? You can use these terms for the CBSDs. So what is unique to CBSDs in case of CBRS? So the CBSD needs authorization from SAS. They need authorization from Spectrum Access System. So if I have only a few CBSDs, then they can communicate directly with SAS. But if I have many CBSDs, I have to use this domain proxy. The domain proxies basically act as an intermediary or aggregation point. So instead of every CBSD independently handling its SAS communication, a domain proxy can manage SAS related communication for multiple CBSDs. The database is basically the memory behind the SAS. It keeps the information the SAS needs about CBSD registrations, locations, spectrum assignments, and action requirements. The SAS uses this information to decide which CBSDs can use which part of CBRS spectrum and at what power. Now, the SAS is the brain of CBRS spectrum management. The CBSD can't simply choose a CBRS channel by itself, right? So it first has to register and request permission from the SAS. But the question comes, how the SAS knows whether important incumbent users need protection. That's why one thing comes into picture, environmental sensing capability, which is ESC. So ESC sensors are deployed mainly to detect protected federal incumbent activity in relevant coastal areas. So when protected incumbent activity is detected, that information is provided into the CBRS coordination system. So the SAS can protect that incumbent. SAS then instructs information to domain proxy and domain proxy that information to CBSD that available frequency is this and you can use only this. So if you're using anything which is related to federal, you have to free that channel immediately. And one more point, that is domain proxy, this SAS are not, they are not replacements in normal LTE 5G network. They are just the additional things we require in case of CBRS or in case of private networks. So if somebody asks me what is additional when I deploy private LTE 5G using CBRS compared with the conventional license spectrum, the most important additional component is the SAS, with the domain proxy being optional depending on the deployment architecture. Now let's understand ESC, environmental sensing capability. So as we discussed earlier that CBRS is a shared spectrum. So we must protect incumbent users such as US Navy radar or defense. So think of ESC as the ears of CBRS system. So it monitors the spectrum and detects protected incumbent activity. So if the activity is detected, if the activity is detected, ESC informs SAS. SAS takes action and the CBSD has to follow the instructions from the SAS. So the SAS may require an affected CBSD to change frequency or stop transmitting on the affected spectrum, or it can also instruct to reduce power. So remember, ESC detects, SAS decides, and CBSD follows. So this is the normal architecture without private networking. So as you know that UE is connected to the small cell. Small cell, like in case of R dot. So this is the small cell provided by Ericsson. We'll discuss in detail in next slides. And small cell is connected to the BBU, and BBU is connected to the core, and core is connected to the service and applications. Right. So this is the normal architecture. Let's again quickly connect the three importance we have already discussed. So one is the SAS. So SAS is basically the controller. So every CBSD must register with SAS, and the SAS decides which frequency and power level the CBSD is allowed to use. It also protects PAL users from the GAA interference. Second one is the ESC, environmental sensing capabilities. So it is a sensing system. It detects protected incumbent activities such as Navy radar and informs the SAS. The SAS can then change the affected CBSD frequency or require it to stop transmitting on that spectrum. Then we have domain proxy. As I said earlier, this is optional. So if we have many CBSDs, instead of each CBSD communicating separately with the SAS, the domain proxy can aggregate and manage their SAS communication. So remember, these three components are very important in case of CBRS. CBSD under control of SAS. So now let's understand how a CBSD actually gets permission to use a CBRS spectrum. So you can say that high level call flow. So first, the CBSD registers with the SAS and requests permission to use the CBRS band. The CBSD can't simply select a frequency and start transmitting, so it requires permission from the SAS. Then the second step is the SAS checks spectrum availability, including incumbent protection, PAL users, and other CBSDs, and potential interference. So based on that information, the SAS provides a grant to the CBSD. The grant tells the CBSD which frequency range it can use and the maximum power it is allowed to transmit. For example, that it may authorize to use 10 megahertz channel or potentially wider bandwidth using multiple contiguous channels depending on availability. So basically, the SAS is telling the CBSD, yes, you can operate, and here is the frequency block or blocks I want you to use. Then we have third step, which is time controlled. The permission is time controlled. The CBSD maintains its authorization through periodic communication with the SAS using heartbeat messages. The heartbeat interval is specified in seconds, and it can be maximum of 240 seconds. Now suppose ESC detects protected Navy radar activity. What it will do? So the ESC informs the SAS, and if our CBSD could cause interference, the SAS can suspend or terminate the affected grant. The CBSD may then have to stop using that frequency and potentially move to the another frequency authorized by the SAS. Now look at the CBRS geographical across the United States. So first we have this federal incumbents, primarily US Navy radar systems. US Navy radar systems. These are mainly associated with the coastal areas. Certain areas are managed by dynamic protection area or EPAs. And this SAS protects incumbent operations from harmful interference. So they are given the highest priority. So if incumbent activity requires protection, the SAS can reconfigure affected CBSDs, which may include moving them to another available frequencies or requiring them to stop transmitted on the affected spectrum. Second we have is the fixed satellite service or the FSS. The SAS also has to consider interference protection from applicable satellite earth stations. Third, we have this grandfather wireless protection zones. Here, legacy operations receive protection under the CBRS transition rules. But the important point is that these protected areas doesn't necessarily means CBRS can't be used there for GAA or PAL. It means the highest priority users must be protected. As I said earlier, CBRS is a shared spectrum, but it is a coordinated spectrum. Shared but coordinated spectrum. CBRS is often called innovation band because it opens the door to many different applications beyond traditional cellular networks. For example, we can use CBRS for fixed wireless access, surveillance cameras, and private LTE or private 5G networks in the smart factories, warehouse, ports, etc. So utility can use it for smart metering such as electricity, water, or glass meters. Another important point is the neutral host. For example, in stadium, a shared CBRS infrastructure can potentially provide connectivity for subscribers for multiple mobile operators. Mobile operators can also use CBRS to add capacity and offload traffic from licensed spectrum using band 48. We also have emerging applications like AR, VR experience, gaming, drones, retails, hospitals, private networks, right? So cable operators can also deploy CBRS network for high traffic locations to offload their mobile traffic and potentially reduce their dependency on their MVNOs partners cellular network. That's why CBRS is called the innovation band. The same spectrum can support many different industries or the business models. Now let's talk about the end user device side. This part is actually quite simple. So if a smartphone, tablet, IoT device, router, or industrial device wants to connect to the CBRS LTE network, it needs to support LTE band 48, which covers the CBRS spectrum. And because CBRS use TDD and even duplexing, the device must also support TDD operation. For 5G NR, the corresponding CBRS band is N48. In case of LTE, it is called P48. Again, what is an EOD? So EOD, end user device, is any device that people use to connect to the private LTE or private 5G network. It can be laptops, tablets, desktop computers, IoT devices, smartphone, all these kind of things. And these devices do not communicate directly with the SAS. Instead, they first connect to a CBSD, which acts as a base station. The CPSD communicates with the SAS, gets its permission to use the spectrum, and then provides wireless service to the end use devices. So the communication flow is EUD connected to CPSD, and if there are not many CPSD, CBS is connected to the SAS. Then we have CBRS antennas. So just like any wireless network, antennas are used to transmit and receive radio signals between the CBSD and the end users. So CBRS antenna operate in the 3.5 gigahertz bands, also known as B48 or N48. So there are different types of CBRS antenna depending on application. It can be omnidirectional or directional. It can be single or dual polarization. It can be have single or dual polarization. So dual polarization antennas improve signal quality and network capacity because they can transmit and receive signals in two different polarization. So some antenna supports CBRS band, while other supports multiple frequency bands. So multi-band antennas allows operators to use one antenna for technologies like LTE, 5G, and CBRS. But there can be sharing between the antennas as well. So most modern CBRS antennas support MIMO such as 2 by 2 MIMO, 4 by 4 MIMO, etc. And this improves the coverage and reduces interference. One thing we should remember, my friends, choosing the right antenna is important part of designing a reliable and high performing private LTE or private 5G network. Before jumping to the next session, let's have a quiz. Can you please let me know the definition of CBRS or the full form of CBRS? Can you give your answer in the chat box, please? Can you please write answer in the chat box, please? Yes. So answer is Citizen Broadband Radio Service. This is the right answer. Second question is private network brings benefit to organization because it has more than one option. So let me give the answer. So they offer higher security and encryption. They do not need license at all. They need license, right? In case of PAL, they need license. So this is wrong. They reduce interference with Wi-Fi and the cellular user. There is no such thing called reduction interference. So this is also wrong. They offer controlled and guaranteed coverage. This is right. They allow organization to have better access control. Yes, this is also right because it will be have a dedicated network. It will be have highly secure network. So what are the two different types of CBSDs? Can you please let me know? Can you please answer this question? Cat A and Cat B. Yes, right answer is Cat A and Cat B. Category A and the category B. What about this? In which band has the CBRS allocated 150 megahertz of spectrum? Yes, right answer is 3.5 gigahertz to 3.7 gigahertz. Thanks, friends, for giving the right answer for all the questions. It means you are very attentive, you are listening, and you are understanding what I am sharing with you. So before we go deeper into RF power calculations or to see the real world deployment, let's quickly understand what a decibel actually means. So a bell is a logarithm unit named after Alexander Graham Bell. In telecommunication, however, a bell is too large for everyday use. So we normally use the decibel. So deci means 1 dB is 1/10 of bell. That's why we are dealing with a power ratio. So we use dB is equal to 10 log 10 P1 by P2, right? So why algorithms? Because logarithm is the inverse of an exponent. For example, 10 power 3 is equal to 1000, but logarithm of 1000 is 3, right? And this thing also you have to remember, dB versus dBm. So dB is the relative ratio, but dBm is the absolute power reference to 1 milliwatt. Okay. So these are some common values to remember. So log 1 is 0 dB. So if we double the power, then it will be 3 dB. If we half the power, it will be negative 3 dB. So always remember, double the power 3 dB and reduce the power by half, it will be negative 3 dB. 10 times will be 10 dB. 100 times will be 20 dB. So can you give me this answer? What will be the factor of 250x? So what will be 10 log 250 by 1? Can you please answer this question, please? Wonderful. Yes. Yes. So 250x, right? So how I will calculate it? So think of it is like 1/4 of 1000, right? Right? So how much is the 1000 is 30 dB, right? So how much will be the 500? I'm reducing by half, right? So when we reduce by half, it will be minus 3 dB. So it will be 27 dB. And if I reduce by other half, it will be 250, right? Then it will be 24 dB. Thanks, guys, for giving the right answer. So can you write yes in the chat box if you understood this concept? Thanks, friends, for the right answer. And as I said that for absolute value, we have to use dBm. And how to calculate dBm? So if it is 1 milliwatt, that will be 0 dBm. If it is 10 milliwatt, it will be 10 dBm. 100 milliwatt, it will be 20 dBm. 1000 milliwatt is 30 dBm. And 2000 milliwatts will be 33 dBm. As you know that when we double the power, it increases by 3, right? So this way you can calculate the dBm. So if it is 11 milliwatts, it will be 10 log 10, 11 by 1. There is no such calculation, right? But you have to 10.4 dBm. But the question is that if it is 110 milliwatts, so how much will be the, can you convert 110 milliwatts into dBm? Remember the concepts. When we're increasing the power by 10, we have to add 10. So 1 milliwatt is 0 dBm. Then 10 milliwatt will be the 10 dBm. 100 milliwatt will be the 20 dBm. And 1000 milliwatt will be the 30 dBm and so on. So if 11 milliwatt is 10.4 dBm, what will be the 110 milliwatts? Can you please answer this question? Again, 1 milliwatt is 0 dBm and 10 milliwatts is 10 dBm. So when we increase the power by 10 times, dBm is increased by additional 10 plus 10, right? So here, what will be the power for 110 milliwatts in case of dBm? Thank you. Yes, the right answer is 20.4 dBm. Okay, guys, thanks for the right answer. And these are the few terms we should remember, that 1 watt is 30 dBm. If you remember these values, you can calculate any values. So 10 watts will be 40 dBm and so on, right? Right? Again, 1 watt is 30 dBm and 0 dBm is 1 milliwatt. So this way you can calculate all these values. And just few more slides and we can wrap up this session. So let's talk about small cells, which are the basic of a private networks. So small cell is basically a low power, compact cellular base station. It is used to improve coverage and capacity in areas where the macro network may not be sufficient. So according to a report, over 12 million small cells have been deployed across the globe. And this number is forecasted to be up to 70 million by 2028. And small cells can be deployed indoors or outdoors as well. Indoors, we commonly see them in the offices, hospitals, shopping malls, and factories. In outdoors, they can be installed on street poles, buildings, or other street furniture. And just like a normal cellular base station, the small cell needs backhaul to the mobile core network. Indoors, this may use enterprise Ethernet or broadband connectivity, while outdoors can use fiber, microwave, or other backhaul solutions, which we have discussed in our previous sessions. That's why small cells are very important building blocks for 4G, 5G, private networks, and the network densification. Now let's understand why we actually need small cells. So there are mainly five key reasons. First one is the coverage improvement. So in some locations, the macro network signal may be weak, especially inside buildings. So we can deploy a small cell closer to the users to improve the signal. Then we have problem with coverage in difficult areas, like in the basement. So places like underground parkings, elevators, warehouses, and deep indoor areas may receive very little or no macro signal. So small cells can provide dedicated coverage in these locations. Third is the additional capacity. So sometimes we already have good coverage, but there are too many users or devices in some areas. So small cells can add extra network capacity exactly when it is needed. Then we have macro offloading. So when a macro site becomes heavily loaded, some users' traffic can be served by nearby small cells, and it helps reduce congestion on the macro network. And the fifth one is private networks in 5G or LTE. For example, inside a factory, this plays a very major role. So we can deploy small cells to create dedicated wireless coverage for robots, AGVs, cameras, IoT sensors, tablets, and other industrial devices. So small cells are not only about fixing coverage, they helps us improve coverage, capacity, network performance, reduce latency, and enable dedicated private 5G activity. Now look at the different types of small cells. Traditionally, we can classify them as femtocells, picocells, or microcells, mainly based on their coverage, power, and the deployment environment. So first is the femtocell. This is the smallest and lowest power type, mainly designed for the indoor environments, such as homes or very small offices. It typically connects back to the mobile network using a broadband or enterprise IP connection. Next one is picocell. So it provides greater coverage and capacity than a femtocell and is commonly used in offices, shopping malls, and other density other high density areas. Then we have this microcell. This is generally a high power small cell solution with a large coverage area. So it is commonly used outdoors in urban areas, campuses, industrial environments, all these things, right? So you can see that power of microcell is highest and femtocell is the least. So let's compare the three common types of small cells based on the coverage, transmit power, and the number of users. So first one is the femtocell. It is mainly used indoors, such as homes and very small offices. And typically coverage is around 10 to 50 meters and power is around 100 milliwatts or lower. And it may support 6 to 20 active users. Then we have picocell. It is commonly used in offices, enterprises, shopping areas, and similar venues. And coverage can typically be around 100 meter to 250 meters. And it can support approximately 30 to 100 simultaneous users. Then we have microcell. It provides large coverage and the capacity. And it generally used outdoors, such as campuses, dense urban areas, and its coverage range is between 500 meters to few kilometers. And transmit power is around 2 to 5 watts, and it can handle hundreds of users. But one thing you have to note that the exact coverage radius, transmit power, and number of users are vendor specific. So the number shown on this slide is just a typical numbers, not the fixed standards. Now, to understand a real deployment of small cell, we have to understand their architecture. So how they are connected end to end. So first we have small cell. You can say that first we have small cell and it has base station plus antenna. It is connected to the Ethernet switch and this is connected to the controller and controller is connected to the core. So small cells is basically a mini base station with its own radio plus antennas, right? And they're connected through Ethernet switches to a controller, which connects them to the core network. The controller helps automatically manage like PCI assignment, transmit power, and interference between neighboring small cells. And they are very cost effective and easy to deploy, especially for smaller buildings. And these are the few advantage, disadvantages, very self-explanatory. So one of the advantages is that they are relatively inexpensive and quick to install. And disadvantage can be it has limited number of frequencies bands, and we may deploy many small cells closer. So we need proper PCI planning, power optimization, and interference management. Right? So this is the theory of small cell. Let's see how we can deploy small cell in the real world example. So generally, we use Ericsson or Nokia for the private networks. So let's see how Ericsson is deployed, and then we will see the Nokia, and then we can wrap up this session. So this is the simple deployment architecture of Ericsson Radio Dot. So Radio Dot is the compact indoor radio installed close to the users, typically on the ceiling. It connects to the IRU, which is indoor radio unit, with the help of LAN cable. So what's the function of IRU? So IRU provides power, connectivity, and aggregation of multiple radio nodes. From the IRU, we connect to the distal or the baseband unit with the help of fiber. And what's the function of baseband? It performs baseband processing and connects towards the mobile core, right? So for CBRS private LTE or 5G, the radio dot is the indoor radio CBSD layer, while the network also require SAS authorization for CBRS spectrum operation. So normal architecture is same, but in case of CBRS, we have to add SAS, ESC, domain proxies as well, in addition to this normal structure of RDOT. So now let's take a, so these are the various kinds of RDOTs models available, but for CBRS, the radio dot available is the 4459. So this is the indoor small cell radio supported B48 and N48. So now let's look at the complete Ericsson radio dot 4459 CBRS architecture. So as you know that the UE is connected to the radio dot 449, which act as a CBSD, right? The dot connects to LAN or Ethernet to the IRU, which is used for aggregation, right? Yes, yes, CBRS is supported by both Android and iPhone. And then traffic goes to baseband and private EPC or 5G core. The question is how much radio dot can connect to one IRU? So there can be 8 radio dots that can be connected to one IRU, but now they are more advanced IRUs that can support 16 R dots as well. But generally we can support 8 R dots with one IRUs. Okay, so the main traffic flow is UE to radio dot, which is also CBSD. Then CBSD is to IRU, then BBU, then core. But for CBS spectrum control, the CBSD must be connected to domain proxy, and domain proxy should be connected to SAS, and SAS should be connected to ESC as well, right? So this is what I was talking about. User equipment is connected to the radio dot, and radio dot is connected to IRU with the help of LAN cable, and with the help of fiber cable, it is connected to BBU and then to the core. But in case of CBRS, this CBSD should be connected to domain proxy, then they will be connected to SAS, and SAS should be connected to the ESC. Friends, are you okay with this architecture? Please write yes in the chat box if you are able to understand this architecture, because for private network, this architecture is very important. Can you please write yes in the chat box if you are able to follow this architecture? Thank you. So these are the few IRU variants for the Ericsson radio dot system. So as I said earlier that IRU acts as the aggregation points between the radio dots and the baseband. So right now in the slide, there are only four IRU types: 2242, 8848, 1648, and 1649. And you can see that they can support maximum 8 R dots, right? And for our radio 4459, these IRU can be helpful, right? So 2243, 2242 doesn't support our radio 449, which is for the CBRS. So this is the basic structure for the R dot. Now let's look at where and how the Ericsson radio dot system can be deployed depending on the size of the venue. The first one is medium to large building. Here, the DU or the baseband and the IRU can be centrally located. Remember, this red one is IRU and the blue one is DU. And from the IRU, we distribute the radio dots to the different areas using LAN cabling. So this is a very simple architecture for enterprise building. Then we have large to very large buildings. So we can still keep the DU centralized, but distribute multiple IRUs across different floors or sections. And each IRU then connects to the multiple radio dots. So they give us final scalability and makes cabling easier for the large buildings. Then we have this subtending nearby RBS. So here, baseband resources can be coordinated between indoor and outdoor coverage, which helps provide better mobility and network performance when users moves between building and the outside area. Right? Then we have campus or large venues such as factories, universities, hospitals. So we may have multiple buildings. In this case, we can use centralized DU and distribute IRUs and radio dots across the different buildings. Right? So the overall concept is very simple. DU is connected to IRU, IRU is connected to radio dots, and radio dots are connected to the users. As the building become larger, we can scale the number and we can scale the locations as well. So this concept is very useful for private LTE or 5G, where we need dedicated coverage across the factory, warehouse, campus, etc. That's why I love R dots, because it gives you all the options and you can deploy according to your needs. So this is just the real-time deployment from IBWave tool. So you can say that how the baseband looks like, how the radio unit looks like, IRU looks like, right? So this is IRU. You can see that it has 8 ports, and then this is the radio dot, right? And it has, so this is the maximum power they are getting at this moment. And so this is how it looks like. Then we have this Nokia small cells. So this is the last topic. So now let's look at the Nokia AirScale indoor solutions, or it is also called the ASIR solution. So here it's very simple. UE is connected to the ASIR PRRH. Then it is connected to the ASIR Smart Hub. Then it is connected to the AirScale baseband. And then it is connected to the core network. This only we have to remember. Right? So the ASIR PRH, also called the Shikra Pico remote radio head, is the radio installed close to the users inside the building. And these are compact, low power indoor radios designed for environments such as offices, hotels, hospitals, factories, and the conference centers. And multiple PRH can connect back to the ASIR Smart Hub. So Smart Hub is like an aggregation or the connectivity point. Then we have AirScale baseband, and this is where RAN processing is done. Right? So this is the high level structure which I already discussed. Like UE is connected to RRH, RR is connected to baseband, and so on. Right? This we have already discussed. So now look at the real Nokia small cell design example in IBWave. So on the left, you can see the Nokia AirScale radio system small cell, which is AHFID, right? So this is the model number AHFID, which is configured as a radio transferred in the IBWave database. The AHFID is the actual indoor RF radio or small cell element installed close to the users. So in this example, it is a ceiling mount unit providing cellular coverage inside the building. So for a private LTE 5G development, the same design approach can be used to plan dedicated indoor cellular coverage for factories, warehouse, and all kinds of enterprise campuses. So this is where the architecture we discussed earlier become a practical RF design in IB way. We select the Nokia radio, define its RF parameters, connect the RF path, place the antennas or radio units, and finally run the prediction to verify coverage, performance, sign-up, RSRP, PLAs, dominance over macro, all these KPIs can be verified. Now let's zoom into the Nokia AirScale indoor small cell connectivity in IBWave. So at the bottom left, we can see the AirScale subrack, which provides the centralized baseband RAN processing. And from the AirScale subrack, the connection goes to AirScale indoor radio system hub. The hub acts as a aggregation or the distribution point. From the hub, we distribute connectivity to multiple AHFID units located throughout the building. And here I'm showing the actual distribution of Nokia AHFID small cell in IB wave. On the left, we can see the manufacturer is Nokia. The device type is radio transceiver and the model is AirScale indoor radio system small cell AHFID configured for the ceiling mounting. On the right, under the sources tab, we configure the transmitter parameters. And in this example, the power per channel is 23 dBm. Here, we can see the detailed properties of Nokia HFID small cells. In this particular figure, you can see that we have LTE band 2 and band 66. Antenna has approximately 2.62 dBi gain. Because it is a ceiling mounted, the objective is to distribute RF coverage around the radio across the indoor environment. So these parameters are important in IBWay because they feed directly to our link budget, propagation calculation, RSRP calculation, SINR, RSRQ, all these calculations. So this diagram shows that how we can scale the architecture from just a few radios to many HFIDs, ceiling mountains, and improve our coverage, capacity, latency, and the network performance as well. So these are the all diagrams from the IBWay. So now look at the private 5G vendor ecosystem. So there are many places, there are many players in this space from traditional telecom vendors like Ericsson, Nokia, Huawei, Samsung, to enterprise and cloud private such as Cisco, AWS, all these things, right? So each vendor brings different strengths across RAN, 5G core, edge, and system integration. So the right solution depends on the enterprise use case and the deployment options. Let's see, I have a few questions. So LAN cable is 100 feet. It can be maximum 100 feet. That can be possible. Okay. Okay, Jilang. Okay. Thank you. So this is all from today's session, and we have discussed 5G building blocks. We have discussed all these things, and we have summarized what is 5G, what are the benefits of them, differences, architecture, summary, all these things, right? And in the end, we have seen what is private network. We have discussed small cell in detail. We have discussed CBRS architecture, radio diode architectures, Nokia architecture. All these things we have seen in today's session. Again, friends, this is Gaurav Goyal. I hope you are able to open those 3 links and you can follow me on the LinkedIn as well. Okay, friends, this is all from my side. Thank you once again for joining this training and for giving me your valuable time. I truly appreciate your commitment to learning and growing. Take care of yourself, take care of your families, and always keep pushing forward. Keep learning, keep growing, and continuing surviving for success. Thank you once again for joining the session. Thank you.